Hello, welcome back. So in this video we will prove the Chevalley-Warning Theorem. So let's state it at first. So assume we have polynomials f1 up to fr, which are polynomials in n m variables over fq, and q is equal to p to the n, and we assume that the sum of the degrees is less than n, less than m, excuse me. All right, and let me correct this. Okay, and we, just to clarify, so the degree of a monomial xm em is just a sum of these e1 up to em, and then the degree of an arbitrary polynomial is just the maximum of the degrees of the monomials. Okay, and now let S be the size of the following set. This is the set of the common zeros of the Fi. So this is in Fq to the m, and this is the set where all Fi are 0. Okay, sometimes one could also write just a set where these polynomials are 0 for convenience. Okay, and now the statement of the theorem is that P, the characteristic of the field Fq, divides the size of these zeros. Okay, and now let's prove it. So let's look at the size of the set modulo P. And what's that? I will write a formula here and then I will explain it afterwards. So here we have 1 minus f1 to the q minus 1 of x. Then we take the product 1 minus fr to the q minus 1 of x. Okay, so why is that the case? So let's look at first at these terms here. So f1 to the q minus 1 of x is 0 if 0 if f1 of x is 0 and 1 if f1 of x is not equal to 0. That's just because fq is the splitting field of x to the q minus x. Okay, and similarly also for the other polynomials. And so 1 minus this f1 to the q minus 1 of x is exactly 1 if f1 is if x is a 0 of f1, and 0 if it's not a 0. And now we want to look at the common zeros, so where all Fi are 0. And so we get that this term, this whole product here, is 0 if and only if x is not a 0 for one such polynomial, and it's 1 then if and only if x is a 0 for all Fi. And why do we say this is S modulo P? That's just because we sum over the 1 in this field, and the characteristic of this field is P, so we have to be a little bit careful. This gives us just S modulo P and not S itself. Okay, so that explains that formula, and now with this formula we can prove the remaining parts. So now we consider the polynomial G, which we define just as this product which we've seen before. And now what's the degree of G? Well, by assumption, the degree of G is less than mq minus 1. We don't really care what the degree is, but the degree is at most the sum of these degrees and the sum of the degrees of the Fi is at most m, so this is at most mq minus 1. And now we use the corollary from last time, from the last video, to conclude that the sum over the x in fq to the n, g of x is 0, which is this sum here, so this is 0. So let me show you the corollary from last time. This was this corollary. So if we have these monomials x to the e, where the degree of e is less than mq minus 1, then the sum is 0. And now one just has to generalize this for arbitrary polynomials instead of monomials with, of course, arbitrary polynomials with degree less than mq minus 1. But this is just straightforward, as these are sums of or linear combinations of such monomials, and the sum of these monomials, sum over the elements of fq to the m of these monomials is 0. So this holds also for arbitrary polynomials. Okay, and then now we are already done. That's what we wanted to prove. Okay, and now we have this strange relationship that P divides the size of the set. So why do we care about that? And now let's state another corollary. So let's take the polynomials as before, and we assume furthermore one more condition, namely that all Fi have 0 constant term. And the statement now is that S is at least P. where S is defined as before. The proof is also straightforward. 0 is now a solution of or let's rather say, 0 is a common solution of all these polynomials if we want them to be 0. So 0 is in this set here. So of course this means they're all 0 vectors in fq to the m. And now we can just apply Chevalley-Warning, because we have now at least one solution, but also it has to be 0 modulo p, so S has to be at least p. And in particular, we can apply this for homogeneous polynomials of fixed degree, say, I don't know, maybe we should say k, because that's something we haven't used yet, and then the fi's don't have have 0 constant term, so we can apply this, and this gives us points in projective space. And so that's the reason why we care about this. So this gives us points in projective space, and one can use this in algebraic geometry. So let me think. I think that's what I wanted to say in this video. So that's it for today. Have a good day and see you next time. Bye.